Hi, folks. We're starting the section on bases. Let's go ahead and get started. So let's talk about definition here. The set of vectors is a basis for Rn if the vector both spans Rn and is linearly independent. Um, we've seen that that can happen, that we can have a set that does both. Um, if we have that, we call that set a basis for Rn. So some examples. Do these vectors form a basis for the Rn? So in this case, this is going to be an R2. Um, and if I look at these two vectors, um, it looks like they're going to be linearly independent. If I try to put this into echelon form, row 2 minus 2 row 1 gives me 2, 1. 1 minus 2 is, or 2 minus 2 is 0. 4 minus 1 is 3. And we have a leading entry in every row. And so this set spans R2. And we have a leading entry in every column. And so this set is linearly independent. And so this is a basis for R2. Let's look at the next set. Can this set be a basis for R3? If we try putting this in echelon form, we will take row 2 minus row 1 and row 3 minus row 1. 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 1 is negative 1. 1 minus 1 is 0. Negative 1 minus 0 is negative 1. Negative 1 minus 1 is negative 2. And now we have to eliminate this entry, so we'll take row 3 plus row 2. That's going to give me 1, 0, 1, 0, 1, negative 1, 0, 1, and negative 1 is 0. Negative 1 and negative 2 is negative 3. And we have a leading entry in every row and every column. And so this is a basis for R3. So this one's a basis. Let's keep going. This is not a basis. I don't need to do any row reduction, but it has too many columns. There's no way that I can have a leading entry in every column. So it's not a basis for R3. Let's look at the last one. This is already in echelon form. In fact, it's our standard vectors E1, E2, E3. Not only is this a basis, we call this the standard basis for R3. This is a basis that we're used to. The x-axis, the y-axis, and the z-axis are represented in these three vectors. Let's move on. We have a proposition in the book that a set of vectors forms a basis only if the matrix that we get by putting the vectors into matrix and row reduce it is row equivalent to an identity matrix. The identity matrix, again, we saw this a couple of days ago, is the matrix that has the standard basis vectors for its columns. Because the columns of A are both a spanning set and a linearly independent set, there must be a pivot in every row and every column. And that can only happen if our vectors form a square matrix. If it's not square, we'll either run out of rows first or columns first. So doesn't mean that every square matrix is a basis, but if it's not square, it is definitely not a basis. All right, let's move on. Every basis for Rn defines a coordinate system that we could use in place of the standard coordinate system for Rn. We have seen problems like this very early in the semester. We're going to study this a little bit more closely now. So we're going to look at this example. Our basis is the vectors 2, 1, and 1, 2. And we're going to have a vector whose coordinates in this coordinate system, in the B coordinate system, are 2, -3. And the way that we'll write that is we'll write that the vector, and then as a little subscript, we'll mention that we're not using standard coordinates, but we're using B coordinates, or 2, -3. So let's sketch this vector. Let's see what we're talking about here. So here's our x-axis. Here's our y-axis. Our basis is now the vector 2, 1. That's our first vector. And 1, 2, which is 1, 2, that's our second vector. Since we're working in this alternate coordinate system, 2 doesn't mean 2 units in the x direction. It means 2 units of v1. So this is going to be 1. And then the second one is going to take me out to here. So that's 2 times v1. And then the -3, instead of being -3 in the y direction, is -3 copies of v2. So v2 points up. It's 1 to the right and 1 down. But I'm sorry, 1 to the right and 2 up. -3 of these, we're going to go back to the left and 2 down. So that's got to be 1 of them. Then back to the left again and 2 down again. And then back to the left and 2 down a third time. And that's -3 copies of v2. And when we're done, we ended up at the point 1 and -4. And we can check that by taking 2 copies of 2, 1 and -3 copies of 1, 2 and adding these together. This is going to be 4, 2 plus -3, -6. 4 and -3 is 1. 2 and -6 is -4. So these are the standard coordinates. In the alternate coordinate system, in the B coordinate system, we're going 2 units of v1 and 3 units backwards of v2. And that gets us to the same location as if in the standard coordinate system we just did 1x and -4y. All right? Let's try another example. This time my basis is 3, -2 for my first vector and 2, 1 for my second vector. All right? So my first vector is 3, -2. And my second vector is 2, +1. And in problem 1, we said that in this alternate coordinate system, not our standard coordinate system, my vector is -2, 4. And so that's the vector that we get if we take -2 copies of v1 and positive 4 copies of V2. So that's going to be 1, 2, 3, 4. What point do we end up with after we have done that? What are the standard coordinates of V? Now, this means standard coordinates because there's no little subscript b after this. Well, we can figure out what this linear combination is by taking negative 2 V1 and 4 V2. So negative 2 times 3 negative 2 and 4 of 2, 1. So let's see what we get. We get negative 6 positive 4 plus 8 4. And that adds up to positive 2 8. So I didn't draw this very well because it should have been a little bit over the negative 2. But these are my standard coordinates. So again, in the alternate system, we can go negative 2 along V1, positive 4 along V2. That gets us to a point. But we could also just go 2 in the x-axis and 8 in the y-axis, and that gets us to the same point. These are my standard coordinates. So we have two different ways of addressing the same point when we have a basis. All right. Same problem. Let's go the other way around. What if we have the standard coordinates, 3, 5, and we want to find the alternate coordinates? So what this means is that there is some number s that we can take that many copies of 3, negative 2, and some number t, and we can take that many copies of 2, 1, and the result is going to be 3, 5. Well, this is just a system of equations. 3s plus 2t is equal to 3, negative 2s plus t is equal to 5, and we know how to solve a system of equations. That's just taking the vectors 3, negative 2, 2, 1, augmenting with the vector that we want to solve for, 3, 5, and solving this system. All right, so we can do that. We'll need to eliminate this negative 2. So we're going to do row 2 times 3 plus 2 times row 1. That's going to make 6's cancel. So 6 and negative 6 and positive 6 gives me 0. 3 times 1 is 3. 2 times 2 is 4. 3 plus 4 is 7. 3 times 5 is 15. 2 times 3 is 6. 15 plus 6 is 21. So now the bottom equation tells me that 7 times t is 21, and so t is equal to 3. And now if I plug that into the top equation, 3s plus 2 times 3 is 6 is equal to 3. So 3s is equal to negative 3. And so s is equal to negative 1. And so we need negative 1 copies of 3, 2 and positive 3 copies of 2, 1. And that should check. If I take negative 1 of these and positive 3 of these, that's going to be negative 3 plus 6 is 3. And positive 2 plus 3 is 5. And so that checks. And so these are the alternate coordinates when these are the standard coordinates. So summarizing up what we just did, if we want to convert from alternate coordinates to standard coordinates, we just multiply out a linear combination. For example, if the alternate coordinates were st, then I just calculate what s copies of 3, negative 2 are, and t copies of 2, 1, and the answer will be my standard coordinates in V. To go the other way, to convert from standard coordinates to alternate coordinates, we will augment a matrix and solve. So for example, I would take 3, negative 2 and 2, 1, augment with whatever matrix we're trying to solve for, and then solve that, and that will get me the solution that we want. So one way is just multiplying a combination out. One way is augmenting a matrix and solving, but we know how to do both of these techniques. Okay, let's move on. This is going to be short, I think. A subspace of Rn is any subset that is a span of a set of vectors. So a basis has to be in both a spanning set and a linear independent set. For subspace, we just need a span. We do not need the set to be linearly independent. So for this example, why is this a subspace of R3? Well, by definition, a subspace is a span, and this is a span. It's a span, so it's a subspace. That's super easy. If you can show that a set of vectors is a span, is a subspace in this example where I'm telling you that it's a span. So it's automatically going to be a subspace. If we tried to describe this subspace, let's talk about it. Span is the set of all linear combinations. So it's all combinations of these two vectors. But these vectors, 1, 0, 0 is a vector in the x direction. And 0, 0, 1 is a vector in the z direction. And if I can take as many copies of 1, 0, 0, including a negative number, and add to it any number of vectors in the z direction, then what I'm going to get is I'm going to get the xz plane. And so this subspace is a plane. It's the span of two vectors. I have two free variables here. One multiplying this vector times s gives me the line that goes through 1, 0, 0. Adding these combinations to it as well means that then from any point on the x direction, I can then move in the z direction as well. And that's what gives me a plane. So it's a subspace because it's a span, because the problem straight up tells us it's a span. And then we can describe this subspace as the xz plane in R3. Let's do one more. Why is, and this should be yeah, I've got my brackets messed up here. There we go. Let S be this set here, where S and T can be any real number. Explain why S is a subspace of R4. Well, I'm going to take this vector here and separate out the S's and the T's. This is S times 4, 2, negative 3, 0. And T times negative 3, 1, positive 3, 1. That's what that splits up into, but that is just a set of linear combinations, and that's a span. It's a span of 4, 2, negative 3, 0, and 3, 1, negative 3, 1, 3, 1. And now that we know that it's a span, all spans are subspaces. In this problem, I didn't straight up tell you it's a span, but we can separate out the s's and the t's and form this linear combination, and that's how we know that we are looking at a span. So how would we describe this subset? I can't draw R4 for you, but this here is some vector in R4, and the S tells me I'm taking all of the multiples of that vector. That single vector would generate a line in R4, but then the second vector points in some other direction. And what it's saying is now I can add to any point on this line, I can add positive or negative multiples of this t vector, and that creates a plane in R4. And so if I'd had to describe the subspace is a plane in R4. All right. In the next next video, we're going to look at subspaces in much more detail, and we'll answer some more questions about subspaces. Thank you for coming. You have a great weekend. Take care.